here. So today we're going to talk about two predictive modeling techniques. The first one is principal component regression, and the second one is random forest. So our goal is to learn about for random forest, we'll learn about the decision tree, how random forest works for both continuous and categorical outcomes. There is often a misconception that decision trees and random forests can only work for categorical outcomes. That is not true. And we'll learn how to implement random forests using R and make predictions, and how to obtain the feature importance or the sharp values to interpret the random forest prediction. And we'll also learn about principal component analysis because many of the times we have collinearity among predictors, and PC regression is one of the very important tools to deal with this kind of situation. We'll also learn about PCA, principal component analysis, in this process. We'll first learn about PC regression first. So this PC regression is especially helpful when we have collinearity among the predictors. So what does collinearity mean? It means that basically some predictors can be expressed as some linear combinations of the other predictors. For example, if you have one predictor that's roughly this just a scaled version of the other one. For example, if you have weight in pound as one predictor and weight in kilogram as one predictor, those are exactly collinear. And there are situations where they're almost collinear, but almost the same, but not exactly the same. For example, you may have biomarkers from the same panel that because of the chemical properties, the biological process, they may just strongly correlate with each other. So collinearity may arise in those kind of situations. And there are also situations when you can also you can express one of the predictors with a linear combination of the others. This describes a more complicated correlation across the predictors. So these are some specific examples of how collinearity can happen among the predictors. If you have a predictor that is another type of transformation, but not linear transformation, for example, if it's an inverse or if it's a polynomial, then this is not collinear. They're still strongly related, still redundant information to some extent, but this is not collinearity. Collinearity describes the linear connections between the predictors. So the collinearity happens a lot in biomarker assays. For example, in gene expression, a lot of the expression of the genes are correlated with each other. And in our case study 1, we'll have BAMA where antibodies can be very correlated with each other. For example, if you do an assay of the abundance of the immune cells, then the composition, they will definitely be collinear because the summation of the composition of all immune cells, that is going to sum up to 1. So one of the immune cell can be expressed by the others. And this also happens in my research area where microbial cells, the bacterial recount. If you think about a community of microbes, they also need to, the proportion of each bacteria, they also sum up to 1. So a lot of real world scenarios will involve collinearity. And the more predictors you collect, the more likely you are going to run into collinearity problems. So we'll go back to the case study here. In the case study, in the first case study, we have the BAMA assay that has a lot of predictors, and we are going to group them by their type. And so these groups are going to be used when we talk about the PC regression. And if you look at the correlation between these markers, here is a heat map of the markers, correlations of the markers. It's cropped somewhere, but you can see there are these large chunks of red on the heat map, indicating those markers are strongly correlated with each other. The labels here are not well matched because the font is too large. So the number of markers is definitely longer than what is showing here. I need to make the font smaller to make the rows match with the names. Do not really rely on the labels here, but the general idea is the message is still here. You can see many of the markers being strongly correlated with each other. And if you put all these correlated markers in the predictive modeling, ignoring the correlation, what will happen? So the consequences will be you mostly likely will have very misleading or unstable result. For example, if you have exact collinearity, if you have both the weight as in pounds and weight in kilograms, if you have both in the predictors, then you will have, if you run linear regression, you will have one row that's NA because you have one redundant predictor. If you put the proportion of all immune cells in the linear regression, you will also have the last row being NA because the last row can be expressed as the composition of the first few immune cells. So exact collinearity basically means that you have redundancy, pure redundancy in the predictors, and one of them, at least one of them, is not going to have a predictor. This is just one straightforward, simplest scenario where the two predictors are exactly the same. Then there's no identifiability between the coefficients beta for the two exactly the same for the two same predictors because you can reallocate values between beta 1 and beta 2 without changing the modeling of the data. So exact collinearity makes it impossible to estimate some regression coefficients and make the interpretation of the coefficients difficult. The second consequence is when we consider when we learn about the interpretation of a regression coefficient in linear regression, we talk about how it's accounting for the effect of others. So the interpretation for a predictor x1 is that coefficient beta 1 quantifies the change of your response variable when the predictor is increased by 1 unit while other predictors stay unchanged. But if you have strongly correlated collinear predictors, then that thing is not really feasible because when you change x1, then the other predictors, for example, x2, is hard to keep unchanged. So the interpretation can be a little tricky. And the third is that this is more problematic. You will have actually very unstable estimation of the coefficients and the p-values. So here is an example. I'm going to put, because we have enough sample size, the high dimensionality here is not a problem. So I'm going to put all of the predictors in regression, all the CD4 all the way to, so it's 100 markers. And these 100 markers, I use the paste function to paste them together to put in the formula. This is a formula, and I will use this formula in the linear regression naively. And if you look at the outcome, all of the p-values are 1. There's still enough degree of freedoms, but you see the residual the residual is basically 0. So I'm basically having a perfect prediction of the outcome, but none of my predictors are significant. And if you use just the CD4 variables as predictors, you will have a different outcome where some of the predictors are actually associated with the outcome. So the high dimensional problem here, if you just use it naively, you will run into this situation because many of the predictors are very correlated with each other. And a lot of them together will make the regression model estimation very unstable, and you will see these insignificant p-values, even though the predictors are actually associated with the outcome. It's just the model is confused. You have so many predictors collectively contributing to the outcome, and they are very correlated. The model cannot really tell which one of them is the important one. And if you account for example, if you have a pair of predictors, both are very important, accounting for the effect of one, the other one is not important. So that multiple linear regression thing with both predictors is going to be really confused about which one is significant. And if you have a lot of them, you will see none of them being significant, even though they are actually informative of the outcome. So if you look at regression coefficients, for example, this CD4 107 thing, the coefficient, if you look at the marginal association between this marker and HIV at 28 weeks, I think we're doing the logistic regression here. Yeah, so it happens the same for logistic regression and linear regression and many linear modeling. The collinearity is going to have the same effect. If you look at the sign of the effect, this is positive. But if you go back to here, I think it was which one? One, two. Yeah. So if this is a predictor that I marked, if I run it with all of the CD4 markers, then it has a significant effect and the coefficient is pretty large. If you just run it alone, it's going to have a non-significant effect that is very small. And if you go back here, I think this was this one. No, not this one, 107. This one. So this one is changing the coefficient estimate again. And the change is actually pretty big from between runs. And in some of the situations, you actually see the sign flip. So if you run it with a limited set of predictors, the sign may be negative, but if you run it with a lot of correlated predictors together, the sign may be another sign. And that's because you're accounting for the effect of the remaining predictors. And if the remaining predictors are strongly correlated with your target of interest, that accounting for that effect will change the effect of your current predictor. That's the inherent nature of linear regression with multiple predictors. The effect, the coefficient for each predictor that accounts for the remaining predictors. If the remaining predictors are strongly correlated with this one, then you will have the effect being the marginal effect and the effect accounting for others. Those two effects will be very, very different from each other. So collinearity is going to make your estimation and p-value for a given predictor very unstable, sometimes even flipping the signs. And how do we detect collinearity? When you have a large set of predictors, manually or visually spotting those correlations can be hard. One way to do it is to make a kind of a heat map to understand what is the correlation structure. If the correlation structure is actually artificial, then you probably spot it from the heat map and then fix it using some non-data driven way. But if you don't really know how to fix it before analyzing the data, then you can use the detection of collinearity and PC regression to fix it. So how do we use a number to represent collinearity is this quantification is called the condition number. So it's defined based on the correlation matrix of the predictor matrix. When you have a predictor matrix, it's sample by feature. The correlation matrix is going to be feature by feature. And the condition number is the ratio of the largest singular value over the smallest singular value. So singular value is comes from the singular value decomposition of the correlation matrix. It's characterizing some very basic properties of a matrix, and the large gap between the largest singular value and smallest singular value means that there's strong collinearity across the predictors. So the larger the condition number is, the more collinearity there is in the data. And traditionally, there's a rule of thumb. If you have the condition number that's larger than 15 squared, then it's considered to be harmful enough. So how are we going to get the condition number? You can use the kappa function on the correlation matrix. If you use the exact equal to true, then it's going to calculate the exact condition number without any statistical approximation. So the condition number, you can do it on the correlation matrix, and you can also do it on the scaled data matrix. Remember to remove your outcome when you try to do this, because you don't want your outcome variable to be part of the condition number calculation. And this, if you do it on the correlation matrix, you compare it with 15 squared. If you do the condition number on the original data matrix scaled, if you use the original data matrix, remember to scale it. With the correlation, you don't have to. If you do it on the data matrix, then you compare it with 15, because this is going to be squared number of the first condition number on the correlation matrix. This is going to be a squared version of the second condition number. So this is just like a rule of thumb. If you don't really know if collinearity is a strong problem in your data set, then you can check it. For our specific example, the condition number is pretty big. So we have a serious collinearity problem. So there are multiple solutions for collinearity. If you can manually remove some of the highly correlated predictors, just for example, some of them can be a representative or a proxy of the other variables, then you can remove the ones that are less important and keep the ones that is more interpretable. So there's a room for manual correction if you know where the collinearity come from, and if you can manually if you can identify the few predictors that can be removed. And then you can also linearly combine those highly correlated predictors. For example, you can add them up, add all of the markers under the same pathway, add them up, or use principal component analysis to do some linear combination of them, and then use the linear combination as predictors. And you can also use partial least square. That is not covered here, but it's an alternative solution to PC regression. In some other situations, you can also find ways to aggregate them using more domain-specific techniques. For example, in gene expression, when you have thousands of genes, you can, and many of them are strongly correlated to each other, you can mitigate part of the collinearity by aggregating the genes into pathways. So the genes falling in the same pathway, if you have some belief that they behave very similar to each other, then they can be aggregated using, for example, some pathway analysis tools like single sample GSEA to aggregate them into pathway scores, and then use the pathway scores as predictors instead of all of the genes. But if you do not have domain-specific ways to combine them, then PC regression is a great way to go. If you do not address the collinearity problem and directly use them in linear regression, can you do variable selection through penalized regression or stepwise regression? The answer is not really. If you put all these correlated collinear predictors in stepwise regression, your end product, so stepwise regression is going to do a variable selection, stepwise step, for example, forward selection or backward selection. And that result is going to be strongly dependent on what your starting model is. Because when when two predictors are strongly correlated with each other, starting with one predictor in the initial model versus the other will actually give you very different end product, because if you have one in there, you will never choose the next one, and vice versa. So the whole stepwise regression path will be very dependent on what you put in the initial model. And you don't want your result to be dependent on on an arbitrary thing like that. So stepwise regression for very collinear predictors is not going to be stable and trustworthy. If you use penalized regression for a data set with strong collinearity, it will also cause some trouble because the model is going to be confused on which predictor to select when they are very correlated. So basically, many of the regression models, they assume that the predictors can be distinguished from each other. When some predictors are very similar to each other, many of the models, they cannot really tell the difference between those two. And same for lasso, it just cannot tell which one of them to select, and it can be very sensitive. For example, if you run it with the first half of the data set, it may select one predictor, and if you use the other half of the data set, you may end up with the other predictor selected. And it's going to be very sensitive to how you run the cross-validation, how you split the data set into training and testing. And removal of one predictor or removal of some observations is going to make your result very different. So you would not want to run stepwise regression or penalized regression before you face a collinearity problem. And that's where the principal component regression come into play. Before we introduce the regression, we'll need to first understand what is principal component analysis. So PCA is a very common and useful tool for data analysis in general. I'm not going to give you a formal definition of PCA, but we'll talk about the intuitions and emphasize on the use of PCA in the context of principal component regression. But PCA has a lot of other uses. For example, visualizing the batch effects across data, identifying the major source of variation in the data. So it is a very useful concept that we should all do our best to understand. The intuition of principal component analysis is that it's going to look for the largest source of variation in the data. Let's first look at two variables. These two markers are quite correlated with each other in our BAMA dataset. So if I put both of them in the regression, it's going to be very unstable. If I try to combine these two variables into one, I can add them up. I can use one of them I can use the other. But what is my best choice? I can use any combinations of those two. But what is my best choice? PCA is going to look for a linear combination weighted between the two variables such that the weighted average of the two variables is going to have the maximum variance. And of course, I need my weighted combination to be constrained so that I don't blow this up. I can always multiply A and B by 100 and make my variance super big, but that is not meaningful. So I'm just going to look for a weighted average of them, keeping the same scale by constraining the weights so that the weights have a L2 norm of 1. The scale of the variable is going to be maintained, and I want to look for that linear combination that has the maximum variance. So why maximizing the variance? Variance is the spread of the data. The information that comes from the spread. If everyone is the same, then there's no information. The information comes from variations, how people are different from each other. So by looking for the largest variance direction, you're looking for the largest information source. And so we're just going to look for different linear combinations, and here is the maximum. So along this direction, this is basically x1 plus x2, and then scale to the original, and then scale to the original scale. So the variables originally have two dimensions, these two variables, and they are now projected onto this linear combination, red line, and our new variable will be these values. So this is the smallest value of my PC component. This is the largest value of my PC component. These are my observations after I do the linear combinations. So this is just dealing with two variables. And the reason why we have x1 plus x2 is because we have scaled them to be to have the we scale them to have the same variance and centered at 0. Basically we standardize them. If you have more predictors than 2, then the result is not going to be a simple linear combination like this. So the way to do the PCA is there are two ways. The first way is through the SVD decomposition. So PCA is often implemented through the SVD decomposition. Those two are two sides of this same thing. So to do it, you need to first do the scaling of the data matrix, but I think this is already scaled or something. Yeah, I think this is already scaled. So I didn't do the scaling here. We'll talk about the scaling later. So assuming your data matrix is already scaled, then you put it into the SVD function. Then the SVD function will produce a result that has 3 elements in there. The loading is stored in the V element, and the others are the D and V I didn't put here. So the loadings here are actually the coefficients that that we put in the linear combination. So this is the V in the SVD output here. This is going to tell us how we should weight the predictors, the collinear predictors, to produce a linear combination of them such that the variance is maximized. So if you look at the V here for this very simple SVD decomposition, the PCA implementation of two predictors, then these are the weights. And this is just visualizing how these two variables are linearly combined. A very important thing to do here is to scale your predictors to have to be centered around 0 and have a standard deviation of 1. And the reason why we need to do that is illustrated in this example. Suppose that I multiply one predictor by 100. Suppose I didn't scale it. Then this predictor is now multiplied by 100. This one is still the original scale. And if you plot a scatter plot of those two, you will see something like this. So when you do PCA on this data set, you're going to end up with just this direction as the maximum variance direction. Because when you look at the spread of the data, when you that spread is going to be very variable that is scaled differently from the rest, then it's going to really tilt the maximum variance direction. You don't want those artificial variation to drive the discovery of your biological signals. So you would want to remove those artificial scaling factors, make everyone at the same level by scaling into center 1 and standard deviation 1. And then when you do a scatter plot like this, you will know where is the maximum information. So basically the PCA is, this process, we have this visual example here is looking for the first principal component between two predictors. And you can do similar thing for 3 or more. It's just hard to visualize because human beings are not made to understand dimension higher than 3. But the idea is the same. When you have a high dimensional space of a lot of predictors, you are going to have a cloud of data points. Some directions are longer, some directions are thinner. Think about the Milky Way, like some directions are longer, and you would PCA will be looking for that longest stretch of the cloud of data points in that high dimensional space. And after you get the longest stretch direction, that's the PC1, you can remove it and then look for the you can put it on hold and then look at the second direction, that's orthogonal to that first one, but also is going to be the direction that has the largest variation, but still orthogonal to the first PC. So PCA is not limited to just one principal component. It can go for many more components. The way to do it is to first get, for example, the first PC linear combination. This is going to maximize the spread of the linear combination. And after having the first PC, we're going to look for a similar thing, but we are going to constrain the second PC direction to be orthogonal to the first one. So we do not want to, we're trying to use PCA to solve collinearity. We do not want the newly constructed PC predictors to be correlated with each other anymore. So we impose this orthogonal constraint. The second one should not be correlated with the first one. And then we'll do the third one. It's still the maximum variance, but with more constraints because now it has to be orthogonal to the first and the second. So the more you keep going, the more constraints you have, and eventually you can go as far as R, number of components, and R is the rank of the matrix. So this is more linear algebra related. In most of the situations, your R is going to be limited by your number of samples and the number of predictors. The rank of the matrix cannot exceed cannot exceed the number of rows or columns. That's the most you can have. And in many of the very correlated strong collinearity situations, this R is going to be smaller than the number of rows or columns. So you cannot get more principal components than the number of samples or predictors. That's your maximum number to go. Any questions?
Oh, there was a question in the chat. I'm gonna just make sure how to scale the variables.
Oh,
that is, yeah.
Yeah. So
you mentioned about to scale the variables, but I'm not sure that did you mention that before or not?
I think somehow when we talk about the condition numbers, we had one code. Yeah, here. So this is how we scale a matrix. After you apply the scale function to a data matrix, all of the columns will have mean 0 and standard deviation 1.
Yeah, I got it. Thank you.
And for this result, we're also going to have the mean and the standard deviation stored in there. I think this might be a good chance for us to go back to R and show you guys how it's working.
Yeah. Yeah, because I know there's also an option in principal components to make it scale the data.
Right.
Yeah.
Many of the tools we use are now more friendly to the user. So, but still there are some who actually by default does not scale them. Just like penalized regression, principal component regression, they all have an option of scaling the predictors. But I think it's still helpful to be aware of this important concept so that when you use the software, you don't miss that. So here I have an example of this is just a random matrix I generated. And I can do a scaled version of it. And the result is going to be a scaled matrix. And it also stored the mean and the standard deviation, the scale in there. So you can retrieve the scale by doing attribute of the result and then specify if you want the scale or the center, the location, the mean. So you can actually retrieve them from the scaled location matrix, but you need to store it separately. If you put this into a data matrix, then it's going to forget about the center and the scale before scale. So for example, if I have another data matrix, X2, and if I combine X2 with my scaled version of the X, then I cannot retrieve the scale data from X2 anymore. It disappeared after you combine the scale matrix with other data. This one. So we were talking about how to implement how the PCA framework works. Extract one component at a time with the components later orthogonal to the previous ones. But each of the steps will still try to maximize the direction. And the contribution of each PC from that the contribution of each PC to the entire data set in terms of variation is also stored. So here it's stored in the SVD function result in the term B here. So we already talked about V being the weights to the variables. D is the contribution of each PC. And then U is going to store the variable that's already linearly combined. These store the weights, so it's going to have the number of rows that's the same as variables. This is going to have the same dimension as your number of predictors, variables. And this is going to have the same dimension as your number of samples. This is going to call the score. This is the loading. And this is called the singular value. The singular values quantifies the contribution of each PC. If you want to get the percent of variance explained, you basically square the singular values and then divide it by the sum of all the sum of squared singular values. So this is calculating the percent of variance explained. The first singular value squared over all of them squared and summed up, that's going to be about 60%. So the first principal component, I'm actually using just these 5 variables as input. I'm doing a PCA with 5 variables, and the first principal component already explained 61% of the variation in the 5 variables. And the last principal component explains the smallest percent of variance. If you want to narrow down the number of predictors from 5, because many of them are quite correlated, you can probably just use the top 3 PC and still explain about almost 90% of the variation. And this loading matrix V is going to store the rotation, the weights you apply to the variables to obtain the linear combinations. And this to obtain the score, the variable that's the variables already linearly combined for each sample, you can use, this is a very statistician manual way to do it. Just to show you the concept, later you will see a more intuitive version. So this is multiplying your data with the loading. This is doing the linear combination of all of the variables using the weights stored in V. You're going to get the linearly combined variables that's here. So the rows are going to be the samples and the columns are the PCs. This is the first PC, second PC, and we will have the value for each sample. These are the operation here I gave you is a very back of stage, take it apart type of illustration of PCA implementation. You can definitely use a more convenient way, which is the PC comp function. With this function, you can just you can obtain the singular values by doing a square root of this compartment of. So the singular values is not directly stored here. You will have to scale it by the number of samples. But this is going to be the singular values, exactly the same as what we did here. And this is the rotation matrix, which is exactly the same as what we have for the V. This is storing the weights. The rotation stores the weights. These are the loading, the contribution of each variable to the PC1. So this is saying that in PC1, The last variable contributed very little, but the first four variables contributed mostly equally. And for PC2, this is the last variable has the most contribution, and the first few variables didn't contribute much. And in PC3, the third variable contributed most, and then the fourth variable, and then the first. So the magnitude in the PC weights, the rotation matrix here, is the loading, rotation, many names. They're all referring to the same thing. These weights are going to tell you for this PC which variable contributed the most. And then to get the variables after the weighted average, you will use the X component in the result. This is getting the single values, this is getting the weights, this is getting the score matrix after the PC rotation, the linear combination. So each row will be one sample. And now these five, if you use the first three, then it's not going to be super. These five will be independent, will be uncorrelated. They are not collinear anymore. If you can use them as predictors without the collinearity problem. And if you only want to use the most useful information, you can use the top three that explain more than 80% of the variance. And so PC regression both serve as a tool to deal with collinearity and reduce the dimension of your predictors. If you started with 100 predictors and only a few, like 50 samples, then running linear regression may not be good. It will not be feasible. You can, if you on top of the high dimensional problem, you also have collinearity that you want to solve through PCA, then the PC regression can help you reduce the number of predictors into the top PCs, and you don't have a high dimensional problem after the PCA. And how do we implement the PC regression? You can do it manually by doing PCA and then doing regression like this. So I'm taking the two variables here and using the first PC as a predictor. This is a very manual way to do it. This is not showing up right. So the result is going to say that my coefficient for the first PC is 0.1272. And if you write it out in terms of the original predictor, so what we have here is, so the original, we have x1 and x2. And the PCA is going to tell us that PC1 is basically x1 plus x2, and then scaled by square root, scaled by the, multiplied by this number. So this is what PCA told us. And when we do the linear regression on PC1, it's going to give us y equal to PC1 times the intercept plus PC1. The coefficient for this one from the lecture note will be somehow the data changed. Huh. So let's just the result is minus 0.07. So this is what PC regression does after we get the PC1 of the two variables and use that as a predictor. This is what we have from the linear regression. And if you want to know what is the original contribution from x1 and x2, you can rewrite the PC1 xx1 plus x2 times 0.0707. This is PC1, and then you time the regression coefficient. That will give you the original the coefficient for x1 and x2. So it will be intercept plus the value for that will be minus 0.049 x1 minus 0.49 x2. So these two times together is basically around 0.049. And the PC regression, if you revert it back to the original predictors, it's going to be these two coefficients. So you can actually regress the PC and revert the coefficients back to each of the original predictors. Any question about this part? And you can do a similar thing for more predictors. Basically just rewriting your PC using your weighted linear combinations of your original predictors, you will get the contribution of each individual predictor to the outcome. So when I was doing the whiteboard, I think there was some difference in the precision. The result is similar here. So instead of 0.049 is 0.047. It's just the calculation of the precision here. It's different. So what I did here is to obtain the original coefficients by multiplying the coefficients for the PCs to the weights in the PC. A nice thing about PC regression is that even if you do not want to throw away any of the predictors, when you have you can still use all of the PCs available, and all of the PCs will be orthogonal to each other. So you still face the collinearity problem without throwing away any information in the data. When your sample size is larger than the number of features, then most likely you will end up with at most P number of components. Your number of components may be smaller than P if you have exact collinearity in the data. If you don't have exact collinearity, you will end up with the number of components that's the same as the number of predictors when you have larger sample size in the features. The result is in this situation, when you do not have exact collinearity, your result is going to be the same as linear regression. But running the PC regression will give you more stable p-values for each of the PCs. And here, if I do a linear regression of the first two variables, and do a linear regression of both the PC. So this is using a PC regression with both predictors and specifying I only want one component to be using the coefficients. then this will be the result that we had. That's the same as earlier I showed you on the blackboard. If you do a coefficient with number of components equal to 2, then this is saying I'm using 2 components for the PC regression, and that coefficient is going to be the same as doing a linear regression because I'm not throwing away any predictors. I'm basically doing a rotation of the data. That's instead of using the original 2 predictors, I'm doing a rotation. I'm using another linear combination of the 2 predictors. If I do that without throwing away any predictors, then the PC regression is going to yield the same result as linear regression. But most of the situations when you use PC regression, you actually do not use all of the components because you use PC regression when you have high dimensionality, when you have high collinearity, and you using all of the components doesn't work to solve those problems. You will use when you have a high dimensional problem with not enough sample size, then using the top view of PC will solve your high dimensionality problem. If you have strong collinearity, then the tail of the PCs, the very low ranking PCs, those are not going to represent a lot of variation in your data. They will most likely representing noise in the predictors, and you don't want your noise variables to mess up with the model fitting. So using those variables will sometimes make your prediction even worse. If you want to use the signal instead of the noise, then you do not want to use all of the components in the data. So here is a general procedure of the PC regression. First, you decompose the data using SVD or PC regression and obtain or PCA. So either the function PCComp or SVD will give you that decomposition, and you will get the rotation, the weight matrix here, and you will get the principal components here. And then you will use the principal components as new predictors in linear regression or penalized regression or stepwise regression. After you have those coefficients for the PCs, then you can multiply them back to obtain the coefficients for your original variables. And in this process, you do not have to use all of the components. So you can at most achieve R components. R is the rank of the matrix, but you can use the number of components that's smaller than the rank of the data set. So here is the code to do PC regression with all of the gamma markers. And here I'm just really arbitrarily choosing the top 10 component. We'll talk about the choice for the number of component later. So suppose I use the top 10 components in the PC regression. Then this is doing a binomial, this is doing a logistic regression with the principal components. You put the principal components in the predictors, and then you will obtain the regression coefficients and the p-value for each of the PC components. And then you can convert them back to the coefficients for each of the predictors. And you can see, you might probably be asking, where is the p-value for these? So that's a caveat for PC regression. You can obtain p-values for each PC, but you cannot obtain p-value for each original predictor. You can only obtain the coefficient for them, but not the p-values, because the coefficients for the original variables, this is redundant. There's a lot of redundancy in the values. They are condensed into the PCs and then reverted back. So among all these redundancies, there's not we are testing for the non-redundant information, which is the contribution of each PC. We cannot test for the redundant scaled back contribution of each variable. So that's one caveat. For PC regression, you do not have p-value for the original variables. You only have p-value for the PCs. And this is showing the PC regression for logistic regression. If you use the PCR function, I think that only works for linear regression. And of course, you may have other more complicated scenario where you may have mixed effect models or DeepSeek or those kind of things. In those situations, if you still want to combine the idea of PCA with regression or predictive modeling, then you can use a more manual way to construct the PCA components yourself and then use those components as predictors in whatever predictive modeling you have. So how do we choose the number of components? You probably already seen this somewhere. It's historically people would choose the top few components. Top 1, top 2 for interpretability, or the top few that explain more than, for example, 80 or 90% of the variance in the data. So here is a plot of the variance explained in our BAMA data to obtain the variance explained, obtain the singular values and square them, and then plot the cumulative summation of them, or the proportion of each one of them. So the first one is the percentile variance for each component separately. The second one is the cumulative variance for the top components. And most of the situations you will see them temper down really quickly. And if you specify a cutoff, for example, 80 or 90% of the variance, then this is going to be the number of PCs you use for your predictive modeling later. That's one way to choose the number of components. A more data-driven way is to use cross-validation. So when we choose the number of components here, we're not really considering the outcome. We're just saying among the predictors, what is the number of components we should include to maximum information extracted from the predictors. Nothing is associated with outcome yet. For cross-validation, if you combine cross-validation with PC regression, then the number of components is chosen based on how well the predictive performance is. So here I'm using the scaled version of the BAMA data with only the CD4 variables. And the outcome is the IgG level. And then I'm using a PCR function to run a linear regression version of the PC regression. And when you do that with validation equal to CV, R is going to automatically give you a cross-validation evaluating the number of components, which one of them is the best. So to get the validation plot for the cross-validation, this is the function to use on the PCR output. And you can specify what criteria you want to use to evaluate the model performance. Is it mean square error, predictor over the predictors, or the R square? So because mean square error is more related to prediction, like this is the first one we're going to see. So we're just basically going to see where the mean square error is the smallest. This is going to be the number of principal components that give us the best predictive performance in terms of MSE in cross-validation. This is considering the out of sample prediction, because cross-validation evaluate the performance using testing and without using any of the training samples. So all of the prediction performance is evaluated out of sample. And if you use R-square, some people like to use it. It's up to you. But I personally rarely see R-square used as a criteria in cross-validation. It's just offered as an option here. And if we want to get the regression coefficients for the original predictors from PCR regression, you can specify a component equal to 1 or 2. So in our situation, I think we had oh, is it 1? Yeah, I think it was 1. So yeah. So the data is telling us that using one component is actually giving us the best predicting performance. So among all the 100 predictors, if you want to use PC regression to do the predictive modeling, then using one PC is actually going to have the best performance. Why is using more PC not helpful? Because using more PC will lead to overfitting and actually a decrease of the performance. So if we look at the contribution of each individual predictors, then you can do the coefficient of the PC regression with n-comp equal to 1 that's selected by cross-validation. And then these will be the contribution. They are basically spread out across all of the predictors. So all these predictors collectively contribute to the prediction. And that collective effort can actually be summarized with just one PC. I was wrong about 100 predictors. This is about 20 something predictors. And then for prediction, you can use the predict function as before. You just need to specify what is the number of components you use. Using one PC, the predicted value for all of the outcome is summarized here. If you want to do cross-validation to choose the number of PC for logistic regression instead of linear regression, then you will have to do some manual coding or I don't know, I'm not aware of any R packages doing it yet. There might be some out there. But manual coding is also not so difficult because you're basically doing 2 steps. One PCA, the second step using the PC values for the linear regression. So here is an example. In this one, I'm doing a very customized analysis. Should we take a break? It's been quite long. Okay. Like 5 minutes later, we'll come back to the example. So for the next hour, we'll complete this example and talk about random forest. This example here is more customized version of the PC regression. So many of the times when you have biomarkers, you can probably group them into several function groups. And if you do not have a very domain-based way to aggregate those markers within the same class, then you can use PCA to aggregate them. So this is an illustration. Our biomarkers can be categorized into these 4 groups. This is just illustration, not necessarily biologically meaningful. But suppose these are the 4 groups that we assign the markers into, then you can do PCA for each specific group and use the first PC or the top few PC from each group instead of pulling them together to as the predictors. This might be useful if you do not want to mix the linear combination of the predictors and make it more interpretable. So you can say that, oh, the top PC in CD4 contribute to certain, is associated, but the top PC in CD8 is not associated, etc., etc. So Here, I'm separating the markers into 4 groups, and then I'm extracting all of the variables that fall into these 4 groups. This is separating them. And so I end up having a list of the variables. The list has 4 elements, with each element being a vector of the variables. I have 25 features in CT4 group, 4 features in the IgA groups. And then I can, for each list of the variables, each of the 4 lists, 4 vectors, I will do a PCA. I'm doing a PCA for each of the group. I'm only taking the top PC here. I'm taking the PC from the PCA, but only taking the first PC here. You can, of course, use more than one. And then the PC values are stored in the new matrix. I will use the PC values for each of for the first PC from each of the group as the predictor in logistic regression. And here it's showing that if I look at just the top PC for each group, then CT8 actually has the strongest association with HIV status at 28 weeks. So you can see the flexibility of PC regression here. And if you know how to do PCA and how to extract the PCs, then you will be able to use the PC components for a variety of predictive models. The drawback of principal component regression, as we talked about earlier, the first one is that we cannot get p-values for each individual predictors. We can only get p-values for the PCs. And the second one is that it doesn't really perform feature selection. So you end up with a contribution from all of the predictors, even out some way, but you do not have some of the predictors entirely eliminated. If you want a more sparse version of the PC regression, there's penalized PC regression, but it's not covered here. So all of the predictors are going to be involved in the final model, unfortunately. And also the PC regression, when you take the PCs, it doesn't really consider the outcome. So when you look for the linear combination of X, the predictors, you are only maximizing the information out of X. You're not maximizing the association between X and Y. If you want to do a linear combination of the predictors that best explain the outcome, then you can do something called the partial least square method. And also PC regression is a little sensitive to outliers in the predictors, because when you do the PCA, you're looking for the maximum direction of variation, and having a few outliers can really stretch, it will actually mess up with the extraction of that maximum variation. So some type of data cleaning to remove the outliers can make the PCA process more stable. The standardization of the variables, this is only relevant if you have a method that you manually calculate the PCs for your regression. If you use the PCR function, then you don't have this problem. You can just specify scale equal to true in the PCR implementation. It will scale the variables for you. But if you do a manual version, then you will scale the data set first. So so if you run a manual version, then you would scale the data first and store it in the scaled version, scaled variable result scale here. And then after you do the PC regression, you can multiply these scaling factor, the standard deviation, back to the regression coefficients, because the this is the regression model with the original predictors. If you do a standardization of the predictor like this is removing the mean and the standard deviation, then your regression coefficients become the beta 1 times the standard deviation. Beta 1 is what you wanted. Beta 1 times standard deviation is what you get from PC regression. So in order to get a beta 1, you need to divide the coefficient from PC regression by the standard deviation of your X to get the beta 1. So this is only useful if you try to do a manual version of the PC regression. Any question? So I think the rest of the time we'll dedicate to random forest. This is a very useful and popular predictive modeling method. So the random forest concept, the reason why it's called forest is because it's made of trees, decision trees. So what is a decision tree? Decision tree can be a classification tree or a regression tree, depending on whether your outcome is categorical or continuous. Categorical, then you have classification tree. Continuous, you have regression tree. They're both regression trees, and they're both decision trees. And here is one example of a classification tree. So here, my outcome is going to be the HIV status at 28 week. And I will go through a decision process that uses many of the predictors. So for example, in the first predictor, IgG level, is it higher than 6? If it's higher than 6, I can make a decision yes. On this, if it's higher than 6, then the decision is diverted to this subtree. If it's lower than 6, the decision is diverted to this half of the tree. And then the next decision, I can decide on whether the patient is older or younger. And then depending on that decision, I can go to the next node for another predictor. What is the number of partners? What is the drug use or the status of protected sex? So going through each of the node is going to split your decision, and eventually you will make a prediction whether your whether the HIV status for that sample is predicted as 0 and 1. So if a subject come in, I can just triage that subject in this decision tree, and it will end up with one of the leaves, and each of the leaves come with a decision. So that if the subject end up this part of the tree, then I will predict the status to be positive. Otherwise, it's if it's end up here, then it's 0. The decision tree will provide a partition of the decision space. So all of the subjects, all of the samples will come with a decision. And the classification tree make a prediction using a label. Regression tree is going to make a prediction for the outcome. So all of the subjects in your training data that end up here is going to calculate something like an average to predict a new subject ending here. For classification tree, it's mostly likely that for all of the subject training data that end up in this leaf, the proportion of the majority label will end up being the predictive label of all of the subjects in this leaf. So the decision tree doesn't have to have a continuous or categorical outcome. You can do a prediction of continuous sample by averaging all of the samples ending in this leaf, or you can do a majority vote for categorical outcomes. But this is an arbitrary tree. How do you build a tree that actually do a good job in predicting the outcome? So that will use the concept of node impurity. So for categorical outcome, node impurity is quantified by Gini index. For Gini index it was traditionally used to quantify the wealth distribution in the society. So a higher Gini index means more extreme, it's less evenly distributed, so more extremely distributed. And the lower Gini index means that it's a very evenly distributed wealth society. So and MSE is used for measuring the predictive outcome, the prediction accuracy of continuous outcome. So how do we build a tree based on these node impurity? This is an illustration of how we do it for a categorical outcome. So HIV status at 28 week as the outcome. Suppose we have a node that has these samples coming into the node. So before the node split, we have 125 uninfected subject and 25 infected subject. If you look at their proportions, then you can calculate the Gini impurity in this formula. This is quantifying how even those two are. If the two are very even, then you will have a larger impurity, I think. You want it to be smaller so that the node is mostly just one group instead of the other, instead of evenly split. So the decision you want to make to split the node would be a decision that mostly make one label in one leaf and the other label in the other leaf. I'm giving you two example ways to split the node. In the first way to split the node, I use the decision. I split based on whether the subjects are older than 30 years old. If I do this decision and split all these subjects into two groups, then I will end up with, in the older group, this is the proportion of uninfected and infected. This is the younger group. And you will calculate the Gini impurity for both nodes combined. So the one here is the total, the highest can be. This is the purity in one node. This is the purity in the second node. So the 0.2 here is the proportion, 0.8 is the proportion, and 75 is the number of subjects here. 150 is the total number of subjects. So you're weighting, this is calculating the Gini impurity for each node and each child node, and also weighted by the number of subjects in the child node. And you end up with a Gini impurity after the split. And compared to before, it's slightly better because the split is trying to make each child node to be more to have more in one group, in one label, and compared to the other. So this is one split. And if you do another split here, then you will have a different Gini impurity. Suppose we ask a question, make the decision split on HIV, having an HIV positive partner. This is probably more informative of the outcome. If you answer yes, then you end up with 29 subjects. That is that has 1/3 of them infected. If you answer no, then you will end up with 121 subjects, and only 13% of them are infected. So you can see after this decision split, we have a much better prediction of the infection status, because here in this split you have a more higher likelihood to get infected. So this is a more informative split, and it's reflected in the Gini impurity. So if you calculate it, there's a decrease in the Gini impurity compared to the parent node. So between these two, if you build a tree, then the second split is going to be chosen compared to the first one. And you are going to do this process for all of the predictors. a random subset of the predictors and see which one of them has the best, and that one is chosen as the split, and then you move on to the next split and build a tree. So the Gini impurity was the criteria for the node impurity here to evaluate how to split the tree. And that's for categorical outcome. For continuous outcome, we'll use the mean square error. So basically trying to calculate the sample variance in each of the node and see if that can be decreased. We want the outcome to be more homogeneous in one leaf compared to before splitting. And the tree will continue to grow until you reach a very small number of samples in each leaf, and you feel that this node cannot be split anymore because there are too few samples in there to make any good decision. Or you can stop when the decrease of Gini impurity is too small. Suppose you go through all possible splits of the tree, all possible ways of growing the tree, and the decrease of Gini impurity is too small to be to be worthy of doing the more computation cost, then you can stop there as well. And you can also stop it when the maximum depth of the tree is reached. This is one of the parameters you need to set in the random forest implementation, the depth of the tree, and there's a default. And after the tree is built, you will be able to predict any new samples by putting that sample into the triage, into the decision tree, and see which leaf node, and then predict either the majority vote for categorical outcome or the average of the samples in that leaf. Questions? Please feel free to type in your questions and I can stop later to answer them. So you don't need to rush when you type the questions. You can always come back. So this is the process of building the decision tree. And random forest is the procedure of building a lot of trees and then aggregating them. So the procedure is like this. You draw a subset of the samples from the data set with replacement. This is also called bagging. And then you grow a decision tree using this subset of samples. And then you do another subset. You do this repeatedly. And you will end up with multiple trees. And the multiple trees, each tree will give you a prediction. For example, a prediction of a label or a continuous value. And you will average the result across all these multiple trees you grow from the subset of samples. When you have multiple trees for continuous outcome, then it's just average. When you have multiple trees for a categorical outcome, then you can also average by a majority vote or doing a frequency, a proportion of each label being predicted among all of the trees. The samples that are not used in training the trees are called out-of-bag samples, and the performance of the tree will be done on the out-of-bag samples. So the random forest procedure is more immune to the overfitting problem. And when each subset of the samples is taken from the data set to grow the tree, many of the times the features, the predictors are also only taken a subset, because random forests many of the times are used in high dimensional settings, and growing a tree for all of the predictors can be really costly. So the very efficient and still effective ways to do a random set of the predictors for each random sample. So each tree is grown with only a subset of the sample and a subset of the predictors. But because you are doing a lot of trees, so eventually all of the predictors are still going to be used. This subset of predictors for each individual tree can mitigate the problem where a strong predictor dominate all of the trees, because in some of the subset of the predictors, your strong predictor may not be there, and a tree will be grown using the less strong predictors. But in many of the situations, we don't really know whether a single strong predictor or many weak predictors, which one has a better overall predictive performance. The advantage of random forest is that it can account for nonlinear predictor outcome relationship compared to PC regression, linear regression, penalized regression. Those mostly model the linear effect of predictors, but random forest can model some nonlinear relationship between the predictors and outcome. Because when we do the decision here, even if you have a continuous outcome predictor age, you're not really using all of the values in the age for one tree. You're categorizing all of the continuous variables in the tree. And in one tree, the categorization might have the cutoff of 30, in another tree it may have a 20, in another tree it may have a 40. So it actually accounts for all kind of cutoffs for a continuous variable. And in that process, it's not directly modeling a linear effect of age, it's modeling all kinds of nonlinear effect of age. And it's also more robust to outliers and overfitting, because for outliers, the usage of a subset of samples among and averaging across a lot of trees, that really help reduce the effect of outliers in one fitting. And the overfitting problem is mitigated by using the bagging process, because the tree's performance is evaluated using the out of bag samples. And then it can also handle more predictors than the number of samples. So for high dimensional problems, you can throw them into the random forest and without worrying about like linear regression or logistic regression, you cannot have more predictors than the number of samples. The disadvantage is that random forest has slightly reduced interpretability of the predictors. If you want a p-value, unfortunately, random forest doesn't give you. So the focus is mostly on the predictive performance instead of inference for individual predictors. If you are more focused on the effect size of a given predictor, you want to quantify the significance, you want to test for hypothesis testing, then random forest is not your friend. It's mostly focused on predictive performance. And if your true predictor outcome is linear instead of nonlinear, then using random forest may have a worse performance compared to logistic regression. So basically, if you know what is the relationship, then using that information will help. If you do not know, then using random forest is still okay. It's just using, if you know that the relationship is linear, then logistic regression is going to make full use of that. And also computationally, logistic regression is more efficient than random forest. If you have a large data set, then computation time may be a problem for random forest. And there are some also for random forest, there are tuning parameters that really affect the outcome of the prediction, especially when your signal is pretty weak. For strong signals, the tuning parameters, the hyperparameters are not going to affect much. But for weak signals, then how your tree was tuned using the hyperparameters may really change the accuracy of the prediction. So these are some main tuning hyperparameters you can tune. The first is the number of trees to build. by default is 500. If you want if you increase this, you will have more computation time, but it will be less stable. And the node size, this is the minimum number of samples to be present in each terminal mode. If you allow a smaller leaf size, then the prediction may be less stable. The tree will be deeper. If you make this a larger one, then your tree will be shallower. You will have fewer time, but and a more stable result, but you may not have a high prediction accuracy because you didn't build the tree enough to reach a good reduction of the impurity. So there's a trade-off here. Larger node size may have a more stable result, but less prediction accuracy. And the M try here is the number of predictors randomly sampled at each split. If you have a lot of collinearity problem in the predictor, then you may want to reduce this number so that when building each small tree, you do not have a lot of collinear predictors messing up with the tree. Another concern that you really need to be careful about is the imbalanced data set. So the tree is going to do a majority vote for the leaf node. If a large majority of your data set is one group, for example, in our situation, most of the patients do not get HIV at the 28 week. So in that situation, doing a majority vote at the leaf node will basically predict every new sample as uninfected. And that's not really helpful. So you would want to build a tree that is going to be more balanced between your category, between your label groups. For this kind of imbalanced data set, the tree building can be balanced through the strata option. So that when you do a random subset of the sample to build one individual tree, it's going to subset the sample with emphasize on the rare group so that your subset of sample has a more balanced distribution between the labels, and that subset of the tree is built more balancedly instead of majority overshadowed by one label. And another thing you really need to pay attention to is make sure your random forest know that your outcome is categorical or numerical. So for our situation, the infection status at 28 week, that is coded as 1 and 0. We know that is a categorical variable, but R doesn't know when it's 0 and 1. So if you directly run that with random forest, R may treat it as a continuous outcome and do a regression instead of a classification. So you need to make sure that is a factor as an outcome so that random forest will run classification instead of regression. So here is a prediction using random forest on the BAMA data with HIV status as outcome. And these are all of the BAMA markers. And if you do not do anything about the imbalanced data set, so I have the variable input as the BAMA markers and also these continuous variables as predictors. If you do not do anything about the imbalanced data set, this is the prediction. So on the rows are the observed. So in total, there are 125 uninfected and 25 infected. But when I look at the predicted value, everyone is predicted as uninfected instead of infected. None of them predicted as infected, because when you do the majority vote at each of the leaf nodes, uninfected is always the majority. But you can do a slightly more balanced run of the random forest by specifying the strata. So I'm going to stratify the random samples of the tree building, the random subset of samples in the tree building. This is specifying the strata is based on the outcome variable. You can also strata by other variables if you want to. For example, if you have a very imbalanced distribution of one predictor variable, you can also stratify on that. But we're more concerned about the imbalanced outcome because it's going to mess up with the majority vote. And then you can specify the sample size. So for each tree building, so I'm here specifying for building of each decision tree, I'm going to take 30 of the uninfected and 15 of the infected. So the subset of the samples to build the tree is going to be more balanced. And in this situation, the random forest will return a prediction that's not all prediction with uninfected. So some of them are going to be predicted as infected. Although the prediction accuracy is still pretty problematic, but you can see it's not doing everything that's the same now. For this specific data set, the signal is not very strong. If you have a stronger signal, then stratifying the data set will really make the difference. So here is the wine data. That's another case study we talked about last time. So the outcome will be the type of wines, and the predictors will be the chemical and the visual characteristics of the wine. And here, if I run it without the stratification, because this data set is more balanced, the three types of wines are quite balanced, so I'm going to run it without strata. And this is the predicted outcome. So actually, random forest was able to achieve a very good predictive performance of the wine type. The misclassification on the off diagonals, I only misclassify 4 samples. And you can also run the wine data with the alcohol content as the outcome variable. I'm just using that because it's going to, I cannot find another example within these 2 data sets that has a continuous outcome. So using the wine data, I'm going to predict the alcohol content. Oh, actually, no. There's something. Oh, this is wrong. Oh, this is showing you a wrong way of running it. So the wine type is categorized as 1, 2, 3. And if you run random forest with 1, 2, 3 as an outcome, without specifying it's a factor, then you will end up with a wrong random forest. Your prediction is not going to be the label 1, 2, 3. It's actually going to be a continuous outcome. Even though the prediction performance is pretty good, but you still have a wrong model because 1, 2, 3 are categorical variables. So always remember to make sure your outcome is treated as categorical variables when it should be. And we'll go over the prediction performance, the running of random forest with a continuous outcome that's done in the right way. This is this part of the lecture notes is going to tell you how to do prediction for each individual sample. So after you run random forest, this is the wine data, then you can do predict on the random forest outcome. And if you specify type equal to response, it will give you a bunch of labels. So it's just going to predict each sample as type 1, type 2, or type 3. And if you do it with type equal to probability, it's actually going to do a similar thing as logistic regression, where it assigns a probability for each label. And in our data set, because the signal is pretty strong, so most of the probabilities are concentrated in one label, but in some of the wines, you can see it's more ambiguous between the two types. In those situations, then the probability will be when looking at the probability instead of the exact labels may be more informative. And the classification accuracy, when your outcome is categorical, can be summarized into this thing called the confusion matrix. So on the X are the observed categories, and the columns represent the predicted categories. So basically for the type 3 wine, we did no wrong prediction. But for type 1 wine, we wrongly classify one of them as type 2. So that's for classification trees prediction. For regression tree with continuous outcome, let's first run a random forest with the alcohol content as the outcome. So we're going to predict the alcohol content of a wine using the color and the other chemical properties of the wine and see if we can actually predict the alcohol content. And when you run that, you will so the alcohol content is a continuous outcome. You will end up with mean square error instead of the confusion matrix. This is going to be non-negative, and the smaller the better. And the variance explained is something like R squared. So the larger the better. And if you want to get the contribution of the predictors, then we'll go to the next section. That's the importance, the feature importance, and the sharp value. So this is the random forest, the concept, the way to implement with categorical outcome and continuous outcome, and how the prediction is made for categorical outcome. And for continuous outcome, you can directly use the predict function without specifying the type. I didn't have an example here. And then the prediction accuracy for categorical outcome can be summarized as a confusion matrix. The prediction accuracy for continuous outcome can be summarized into mean square error. So that's how you implement and get prediction. If you want to evaluate the importance of each predictor, then it's there are several concepts that are used in the field. The first one is called feature importance. There are mainly two types of feature importance. You will see the first one more frequently. The first one is permutation importance. So the philosophy is that if a predictor's value is randomly shuffled, if you just shuffle the value of this predictor across all samples, then its association with the outcome should be broken. And this predictor after shuffling should be less useful for prediction. And if it's strongly predictive, if this predictor is strongly predictive of the outcome, then looking at the predictive performance before and after the shuffling, there should be a large reduction of the prediction accuracy before and after you shuffle, you permute the variable, the predictor. So the importance of the permutation importance of the predictor is defined as this difference in prediction accuracy when you permute that sample and evaluate that prediction accuracy in the out of bag samples. And then this importance of the variable is going to be averaged over multiple permutations. So you're not going to be overly rely on one permutation, one shuffling of the permutations. You're going to do multiple shufflings, evaluate the drop of performance, and average over multiple permutations. And the larger the permutation importance is, the larger the gap is between the before and after shuffling. So larger feature permutation importance means more contribution of that predictor to the outcome. And most of the situations you will have a permutation importance that's positive, but there are few situations when it's actually negative, which means that when you shuffle that predictor, you actually improve the prediction. How does that happen? That predictor, when you shuffle, it's not related to the outcome, but it's actually improving the prediction. That's because before you predicted, it's actually that predictor is harming the model performance. It can be due to collinearity. For example, one predictor in the model is already very strong predictor of the outcome. And your guy X is very strongly correlated with this strong predictor. So when you add your guy into the model, two correlated predictor is going to make the prediction worse, and removing your guy from it actually makes it perform better because that strong predictor is already in the model. So when you have this kind of situations with two very strong predictor, you may one being very strong, one being collinear with that strong, but not as strong as that predictor, you may actually end up with a negative importance score for a predictor. So and for categorical outcomes, you will actually have a permutation importance for each categories. So here is an example. If you use the importance function on the wine data prediction, because it has three categories, three types of wines, you will see the first three columns. These are the permutation importance. It's saying that when I classify the wines, alcohol is going to play a bigger role in the accuracy of classifying type 1 and type 2 wines, but a smaller contribution comes from alcohol in terms of the accuracy of labeling type 3 wine. Because when you talk about misclassification, there's a misclassification rate for each category of wines, each label. So there's a permutation importance for each of the labels. The second feature importance is called the mean decrease impurity. And that one is going to be just one number, regardless of whether it's one number for each feature, regardless of how many labels you have. So the concept is when you split the tree, you're trying to reduce the impurity of the nodes. And a larger reduce in the impurity means that the feature you use to split that node is a more important feature. For example, here, this having HIV partner is a more important feature compared to age. So if I evaluate the reduction of impurity for this variable, it's going to have a larger reduction compared to this one. And I'm going to evaluate the reduction of impurity for example, this variable for all of the trees in my forest. For each tree, if that tree uses this variable in any part of the tree split, I'm going to evaluate the reduction of the impurity. And I'm going to average across all trees for this variable. And that average reduction of impurity is summarized as the MDI here. So it's average for across all of the trees. It evaluates how that variable contribute to the building of the tree. And there are two ways to evaluate the reduction of the impurity in the feature importance. One is using the mean when you have a continuous outcome is the MSE. When you have a categorical outcome, it will be the Gini index, mean decrease Gini index. And for continuous for categorical outcome, there is also a misclassification error. So basically for the wine data, the first 3 columns, you will look at them for the permutation importance, and then you will look at the last column, the mean decrease Gini index for the impurity reduction, the MDI. And for continuous outcome, you will look at the first 2 for the permutation importance, because we have 0 and 1 for infection status. And then here we'll also look at, oh, this is not continuous outcome. This is still classification. So the Gini index is the mean, the MDI that I'm talking about. And if you want to take a look at the table here, for example, the G, this is one of the variables with large importance. So it's actually contributing a lot to the classification of both labels. And a sanity check would just look at how it helped with the prediction in terms of the direct association with the outcome. So this is just a sanity check. If I tabulate this variable with the outcome, then it's actually saying that it's going to so it's better than random. So there's 2 infected groups that are actually positive for this variable. This is, I think, 2 infectious, 2 STD viruses. So having those viruses is positively correlated with HIV status. And this is the partner, I think, the number of partners. I forgot which one. I need to look it up again. But for this one, it's also one of the ones that has this one has a smaller importance compared to this variable. And if you tabulate them, you can see that it's actually doing a worse job than the first variable in terms of predicting the outcome. So this is just a sanity check to see if the feature importance actually makes sense. For continuous outcome, this is predicting the alcohol content using the other properties of the wine. You will only have the 1 column for the permutation importance, and the 1 column for the purity, the MDI. And another way of doing sanity check for the predictors is through a scatter plot. Here we use the table function to do a sanity check between 2 categorical variables. If you have 2 continuous variables you want to do sanity check on, you can do a scatter plot. If you have 1 categorical, 1 continuous, you can do a box plot. So this is feature importance, the permutation importance, and mean decrease impurity. You can use either one to quantify the importance of the variables. Permutation importance is more commonly seen. So for the wine data, at least the 2 variables with very strong, very large feature importance, they do have a strong correlation with the alcohol content. The second concept we often see is the Sharpe value. So this is a concept from game theory. And this one quantifies the contribution of a feature to the prediction of one individual sample. The feature importance is an overall evaluation of the contribution of each variable to the whole modeling. So it's not specific to each sample, it's aggregated across all of the samples. But Sharpe value is sample specific. It's evaluating the contribution of each feature to the prediction of one sample. So how does it work? The Sharpe value measures how much a feature is going to shifts the predictive value of a sample from the overall average. So suppose you have for example, for the prediction of a housing market, I think this is like the sample I see the most. So when you try to predict the price of the house, the baseline on average, what is going to be the predicted housing price in the market. That's the baseline prediction. And then for a given house, if the average in the market is, for example, 300K, and then for a given house is 400K, what contribute to this 100K difference? That contribution is going to be decomposed into the contribution from each feature. So for one feature, how much that feature if I include that feature in the prediction, how much is that going to shift the predicted value of the sample from the baseline, the 300 market average? And this shift by the marginal contribution, we're going to evaluate the marginal contribution to the 100K difference for each feature, and that's going to be averaged over all possible combinations of other features. For example, I have 4 square foot. I have number of bathrooms, number of bedrooms, if there is a deck, or if there's a hardwood floor. All those are predictors of the housing price. And I will do all combination. If I want to evaluate the importance of having hardwood, I will do all combinations of other predictors, doing a subset of them, and then combine them with the hardwood variable to do the prediction. And then I will do it without the hardwood variable to do the prediction. And I will evaluate how much that adding that hardwood, so I will evaluate how much the housing price is going to increase if that house has hardwood in the house. So it's going to tell me, having one feature, how much by having that feature is going to change the predicted outcome, the housing price. And positive Sharpe value means that that if that feature increases, then it means that the feature increases the prediction outcome. Having that feature, having the hardwood, will increase the outcome. And smaller Sharpe value means that does not having that feature or reducing value of that feature will give you a smaller predicted outcome. So the Sharpe value is going to be two-directional. If you have super large or super small values, then it means more contributions to the outcome. If you have a Sharpe value close to 0, then it's less important. And the Sharpe value is very sample specific. These should be absolute values. I was talking about as absolute values, not double line, should be single line. So the Sharpe value is going to be sample specific. So for one house that is already, so for one house that is that has hardwood, has cat, has is cat friend is disabled friendly and has a deck, by adding the feature of hardwood or removing it may have may have like 50K improvement of the housing value. But for another house that is located in a different school zone, then having that hardwood may not increase that house value by much. So the SHAP value is actually evaluating that increment for each feature, for each house separately. The SHAP value of a feature may be positive for one house, but it may be negative for the other house. And the when two features, this is a very important property of SHAP value. So when you have two features that are strongly correlated, SHAP is going to fairly distribute the importance between the two. But feature importance is most likely going to give full credit to just one of them. So SHAP value is going to be more interpretable in terms of for those strongly correlated features. And eventually the deviation of the housing price from the baseline, from the market average, that is going to be a combined contributions of all features. So if you combine the SHAP value of all features for a given sample, that's going to be exactly the difference between the predicted value of that house minus the market average. To obtain the SHAP value, you can use the R package RML, if you use the random forest implementation we talked about earlier, then you can use this package. There are other implementations. We're not going to go through them. So if you use this package, you can directly put the random forest outcome in the input. And then this is constructing, this is extracting the result from random forest outcome, specifying where the data come from and what is the outcome variable. And then you can use this package to obtain both the feature importance and the SHAP value. So we'll go. They have very similar syntax. If you want to get the permutation importance from this package, you use feature importance $new. This is going to be a function onto what we extracted earlier here. For classification, you would use loss equal to classification error. For continuous outcome, you will use the mean MAE or MSE, the mean square error, for the loss function to evaluate the feature importance. And here, because the wine type is outcome, we are going to use classification error. And this is the table of the feature importance for all of the for the predictors we use. So the permutation importance can be obtained using this function. And it also provides you a plot to visualize the feature importance. So here, this is just a subset of the variables, and you can see all of them in the plots. One of them has the biggest contribution to the prediction accuracy in terms of type. If you're trying to predict the alcohol content using the other ones, so this is a continuous outcome prediction, then this is the random forest from the continuous to predict the outcome, the alcohol content as outcome. And this is specifying the outcome variable. And feature importance for this run is summarized here. So among all of the variables, color is the strongest prediction, has the strongest prediction for wine, for alcohol content. So these are the permutation importance as before. You only have, this is a global evaluation of the feature contribution. And for SHAP value, that is going to be a sample specific thing. So when you extract the SHAP value, you actually look at a specific sample. So here I'm looking at the first wine. I use the Shapley function, and this is what we constructed earlier using the predictor function. So after the predictor function, I put it into the Shapley function here to get the Shapley value for the first y. The sample size here is the number of times all combinations of other samples, other variables are sampled to evaluate the marginal contribution of that of each feature. So this is tuning point. This is not going to have a big impact on your outcome, if as long as you don't set it too low. The higher it is, the more accurate the Shapley value is. It's an approximation using subsampling. If you have too higher the sample size, then it's going to be slow. So if you want to have a trade-off between so basically the higher the slower, the more accurate, but somewhere in between 50 is a good value to start. That's the default value I think is recommended by the package. So this is the extracting the Shapley value for the first line, and you can see where is the largest ones. So visually checking the numbers is hard, but you can look at the plot. So the wine is a type 1 wine, and for the classification of this wine, proline is going to make the biggest impact on deciding whether this wine is a type 1 or a type 2. So basically, if proline level of this wine is decreased a lot, then this wine is probably going to be classified as a type 2 instead of type 1. And if you look at the Shapley value of another wine that is in the 70 row, that one is a type, I think it's a type 2 wine. So for that wine, proline is not making a lot of contribution in the decision of the classification. It's the color and alcohol content. So for this specific wine, if the color is has a reduced number, then it's more likely to be classified as a type 3 instead of type 2. Similar for alcohol, if I reduce the alcohol content of this wine, is more likely going to be classified as a type 3 one. And you can also do the sharp value for a continuous outcome. Suppose we're predicting the alcohol content, then you just put the predictor. This is the outcome of the predict function here. So predictor function on the random forest outcome, and then put it back in the Shapley value thing. Specify which one you're looking at. For the first one, proline is going to be most predictive of the alcohol content. So so marginally, these are the reasons why we predict the alcohol content at this level. If I have if I have a higher level of proline, then the alcohol content is going to be predicted as higher. And similarly for this is the 70th row, another wine. For this specific wine, the alcohol content is more related to the color. So you can basically see the difference between the feature importance and sharp value now. For feature importance, it's a global contribution of the features, so it's not specific to one sample, but for sharp value, it's specific to individual samples. You are evaluating the contribution of each feature to the prediction of that individual sample. And for feature importance, larger is better, and it's rarely negative, but it can be. For sharp value, you look at the absolute values, and the signs indicates the direction of the influence. For feature importance, the permutation, both of them are faster than SHAP because SHAP is doing it one sample at a time. If you want to do it for all of the samples, it's going to take a long time to run. So most of the times, when you run a random forest, you have a large sample size set. And evaluating SHAP for all of the samples can be costly. You would do it for a targeted sample or a subset of sample or for the most important samples. But for the permutation importance, it's an overall one, and you will see this more oftenly used to describe the overall contribution of the features. So that's all for today. I'm sorry that it took so long.